podcast is brought to you by LMU Munich.
So I've been asked to take you on a tour of some of the technical tools that come together in tackling these leading multi-loop calculations in supergravity. Some of what I'll be talking about will be organizational. Some of this will be apprehending various ways that gravity and Yang-Mills theories are intimately associated. And at the end, I'll briefly close discussing some recent UV surprises and give an update on 5 loops n equals 4 super Yang-Mills. Okay, so the tools. So this organization in terms of cubic graphs, unitarity method, and KLT for field theory allowed these calculations of n equals 8 supergravity through 4 loops by calculating n equals 4 super Yang-Mills, exposing previously unexpected superfiniteness. So I'm going to be talking about KLT and graphy thinking and unitarity. And I'll point out there's going to be some very sophisticated graphy thinking and geometry emerging from planar n equals 4 for the talk right after me from Nima. As an aside, this sort of graphy thinking and unitarity is also very important for collider physics. Besides the fantastic stuff that's been happening at 1 loop very recently, these types of approaches are starting to go after 2 loops and 3 loops. So these higher loop n equals 4 super Yang-Mills calculations exposed a highly constraining structure, a color kinematic duality. It trivially generates gravity theory amplitudes in a graph-by-graph way through a double copy of the kinematic weights. This has led to disentangling KLT in string and field theory and ongoing work in exposing the underlying cause. So I'm going to be talking about color kinematics and double copy. Now, if you're not familiar with the benefits of calculating these constrained systems, it can be helpful to consider a type of constrained poem like a villanelle. So this is Dylan Thomas. So usually when I talk about this, I give a poem, a villanelle by Dylan Thomas. Do not go gently into that good night. It's a great poem. But since I'm in Munich, it's another topic seemed appropriate. And it turns out I have a friend, an old friend from college, who did actually a long time ago write a villanelle about beer. So this is what I'm going to show you. We're not going to read it too carefully because he's a bit of a contrarian, and he was kind of pro this particular American domestic beer. So clearly he needs an invitation to come visit Munich. But what I'd like you to note with this fairly constrained poem with villanelles is that all these, well, that should have been here. All those lines have to be the same. All those lines have to be the same. All those lines have to rhyme. All those words have to rhyme. Years, peers, jeers, cheers, interferes, ears, and all those lines have to rhyme. So what's going on is that you put a minimal amount of information in, and it propagates to a full solution. This is exactly how we're using these constrained relations to calculate a multi-loop. So this is 4 loops. These are all the cubic graphs that contribute at 4 loops. And these relations constrain the kinematic contribution of each graph to be related to just this guy. And so when you go after the information from the theory to build this amplitude, you need to go after the information in this guy in the right way. And the relations propagate that to the entire scattering amplitude. And as a byproduct, you get n equals 8 supergravity, trivially, as a double copy of the contributions graph by graph. So, so the way we organize our calculations are in terms of these cubic graphs. And so for both Yang-Mills and gravity, cubic graphs are completely sufficient. All higher order vertices we can assign to cubic graphs by multiplying and dividing by the propagator. So we mod out by the denominators as scalar propagators associated with, if it was a scalar Feynman graph, you just divide out by that. What's going to be on top is going to be theory dependent. For gravity theories, it's just going to be kinematics, but for gauge theories, it's going to have a color weight as well as a kinematic weight. And so these cubic graphs, each vertex represents either conservation of momentum and also for gauge theories, conservation of color. And so this is a very natural way of making these symmetries manifest, right? So if you're going to go hunting for structure, having a representation that makes conservation momentum, makes conservation of color manifest is a very useful place to do it. So I'm going to, just to give a feel for how this works, I'm going to give a 4-point tree example. Okay, so these are the 3 graphs. They're just relabels of the same graph, S, T, and U. As I said, the 4-point you can assign between these guys. The representation I'm going to show is going to be a symmetric one where it's actually the same numerator function applied independent of labels, so you're just summing over the label. So this is going to be manifestly crossing symmetric. So the color factors you just dressed with FABCs, the denominator, of course, is just the propagator. And this is the numerator you can assign that gives you a gluonic amplitude. You'll see I wrote this in terms of a color-stripped tree. You might think this is a little perverse, and in fact, at tree level, it is somewhat perverse to dress graphs in terms of color-stripped tree. But these are useful functions and ways of encoding external state that you'll see actually makes a huge difference for keeping loop amplitude dressings compact. And you see, this dressing actually makes manifest the antisymmetry. So we require that our numerator factors are antisymmetric. And you can just see how this works. So swapping 1 and 2. This is completely independent permutation, right? All it changes is this side into here. This goes to here, and this goes to here, picking up a minus sign. And similarly, flipping this, it picks up a minus sign right from over here. Okay, so here's a representation, a symmetric representation, a graph-based representation, cubic graphs of the 4-point tree. Now, amusingly, that guy is much more complicated than many 4-point multi-loop numerators for n equals 4 superangles. As you go higher in loop order, so these are the ladder diagrams. These are arguably the most compact numerators. It has this universal prefactor, then encodes external state. And then for each additional rung of the ladder, you pick up a power of a Mandelstam S. And this keeps going. And so, but let's look at so this is 3 loops. This is 3 loops at n equals 4. These are the numerators. These are very nice, calm expressions. This is kind of a clear demonstration that these organizations around cubic graphs are sort of a very manageable way of organizing the information. So how do we know if an amplitude is correct? Somebody hands you an integrand, how do you know if it's correct? And the answer is if it satisfies all d-dimensional generalized unitarity cuts. If you're familiar with unitarity, it's sort of, this is kind of an obvious statement, but if you're not familiar with it, unitarity cuts are a way of comparing contributions from an integrand to on-shell knowledge that you already have by your theory that's made manifest. And so we assume you already know how to write down your tree amplitudes, right? Because we do for these theories, for Yang-Mills and for gravity theories, we completely know the tree amplitude is all multiplicity, right? And so it's recycling this on-shell information and building higher loop amplitudes is the goal here. Why all cuts? Why do you need to, why all cuts? It's so that you leave no graph topologies untouched for contributions to be hiding. And this is how you actually know you're getting the right answer. A spanning set, but so all cuts, that's a lot of cuts. That's too many cuts, right? And so what you want, so the nice thing is that there's this concept of a spanning set. It's any set sufficient to ensure the satisfaction of all cuts, given the theory. And so various theories have absolute bounds for the number of collapsed propagators that can be hiding for the loop momenta that could ever be sitting in the numerator. And so anything above that is nice and overcomplete and guarantees that you're not missing any contributions. Why d-dimensional? Because again, when we're looking for behavior, for divergences in critical dimensions higher than 4, you'll want to make sure you're not missing any contributions. And even when you're dealing in 4 dimensions, we regulate our IR divergences with dimensional regularization, and to make sure you're not missing contributions. You want to make sure that all your cuts can capture everything. Okay, so the construction with graphs. The amplitudes organized around graphs make unitarity cuts straightforward. Using graph isomorphism, it's easy to identify the contribution to a cut from the integrand. So if you have your integrand organized graph by graph by graph, you can look at the topologies that would contribute to this being expanded in all cubic ways and this being expanded in all cubic ways, and only worry about the contributions from those graphs. And anything that's sufficient for verification and straightforward to execute can become a tool for construction. And so this is sort of the spirit of this modern graphy unitarity amplitude construction, is if it's sufficient to satisfy all cuts, and if it's efficient to actually isolate information, and with complex momenta, you can target very precise contributions down to cubic amplitudes, to 3 vertex amplitudes. So targeting very individual contributions. This is what's allowed us to go to fairly high loop order. Now, how do we get gravity? And this is from this beautiful result in 1985 that the information in the string gravity amplitudes is completely encoded in string tree level S matrix. That you have these expressions for gravity tree amplitudes in terms of sums over products of Yang-Mills tree amplitudes. In '85, they did this shortly after the heterotic string. No closed all multiplicity expression. They gave through 6 point. They gave an algorithm that was straightforward for going to higher point in many situations. Fast forward a decade, these guys wrote down the complete KLT relations in field theory. It's a closed form, all multiplicity expression. It was inspired by the tree level relations in the alpha prime goes to 0 limit, and supported on soft limits. They were able to go to all multiplicity. It wasn't proven, but the support on soft limits is very strong, and everywhere they checked, it worked well. So since then, actually fairly recently, has been proven. And so I'm going to show you this expression in a second, and it does make manifest just how scrambled these relations between color-ordered gauge amplitudes and gravity amplitudes can be. But even though it is going to be kind of scrambled through these graph-organized unitarity cuts, it did allow us to climb to n equals 8 supergravity. And so this is the expression, right? The all-multiplicity expression, you'll see, is the sum over permutations of legs here, and then inside that's another sum over permutations. Right? And these are gauge theory color-ordered amplitudes. And these factors here are some nice sums over Mandelstam invariance. There's a lot going on here. But the wonderful thing is that that cuts of gravity amplitudes factorized to cuts of loop amplitudes. So when you had loop level Yang-Mills, you could recycle that into getting loop level gravity theories. So, okay. So these tools can take you to 4 loops. But it can take you a while to get there, and you can develop quite a long beard if you're not shaving until you're done. But it was on this climb to 4 loops that we started seeing the structure in Yang-Mills. And this structure is the fact that you can find representations at tree level where not only do the kinematic factors satisfy the antisymmetry, it was always part of the game, but they can satisfy the same Jacoby relations, the exact same Jacoby relations that the color factors do. So these kinematic weights satisfying the same algebra as these color factors. So this is the sort of emergence, this duality between color and kinematics. And I promised gravity. These color factors are just sitting there, right? So in the gauge theory amplitude, these color factors are just sitting there obeying antisymmetry and Jacoby relations, but now we know that these other objects that can sit there obeying antisymmetry, and Jacoby relations, right? These numerator factors, and so when you replace a color factor with a numerator factor, you get a gravity amplitude in a related theory. So if these guys are both n equals 4 super Yang-Mills, then you get n equals 8 supergravity. If this is n equals 4 and this is n equals 0, you get n equals 0 supergravity. This was proven, this double copy was proven at tree level given color kinematics and KLT by Byrne, Denon, Wang, and Kiermaier a couple years ago. Okay, so what I'm going to take you through is a straightforward algorithm for how to find duality satisfying numerators at tree level. It works for all multiplicity, but we're just going to go through 4-point just to get a feeling for how this works. So you write down all endpoint graphs and all independent Jacoby relations. So here there are only 3 graphs that are n equals 4, and there's only one Jacoby relation. You solve the linear equations of all the set of Jacoby relations, in this case it's 1, to get a graph basis in terms of the Jacoby independent numerators. And it turns out you can always let them be a particular topology at tree level, like half ladders. For 4-point we solve and get that the U contribution has to be the S contribution minus the T contribution. Next step is to expand all the color-ordered amplitudes in terms of their constituent graphs. So here's a colored-ordered gauge amplitude. So color stripped, so the color is gone. These are the numerators and the graphs contributing to the cyclic permutation. There are only 2 numerators left, so we only need 1 tree at 4-point. So this guy gives, this guy's graphs are S and T. So here's the color-stripped amplitude. You write the color-ordered amplitudes in terms of the graph basis, so you substitute in, if necessary, solve the linear relations, and then you're done. So it's just a purely linear operation at tree level to find representations in terms of color-ordered amplitudes that satisfy the Jacoby relations. And you'll notice at 4-point there's this residual freedom. In this guy, this can be anything, and it will still be the correct answer, right? And it will still satisfy Jacoby. So this is complete freedom. And so the previous representation for 4-point I showed you before is also, by the way, Jacoby satisfying, the symmetric one, right? And that's much more involved. You can choose this so that you get a symmetric one, so everybody's symmetric. But in general, to find symmetric representations at tree level involve solving functional relations. Okay, so the features of this is it's completely straightforward to actually get the Jacoby satisfying numerators, and it makes all residual gauge freedom manifest. And since you have amplitude encoded results, your relations are generically d-dimensional and independent of what the external states are. Interestingly enough, the 4-point, so this is just sort of a side note, 4-point kinematic satisfying Jacoby was first noticed by these guys in the late 80s looking at a phenomenological radiation zero lecture week process, but they never looked to see if there was the freedom to go at higher multiplicity to find Jacoby satisfying representations. Okay, since then there's been, since we noticed this at tree level, there's been many interesting ways of writing down tree level color kinematic satisfying numerators. I think an important one is rearranging the Lagrangian such that your Feynman rules actually start making this manifest, right? So you start getting cubic diagrams only, and they satisfy the Jacoby. And the way you do this is you add 0, right? But something that's 0 by color Jacoby that moves terms around. So that's one way. Another way, and this is really slick, is just extracting the color kinematic numerators out of KLT, which again we have an all multiplicity expression for, and these guys showed how to do this, and so this gives an all multiplicity examples of color kinematic satisfying Jacobys at tree level. We're going to hear from Schlatter a little bit later. Well, these guys, using pure spinners and string insight, were able to write down directly local but not symmetric Jacoby satisfying numerators. Montier and O'Connell figured out a way to extract Jacoby satisfying numerators from the self-dual in a straightforward way. And more recently, they've been building effective scalar field theories at all multiplicity to get Jacoby satisfying numerators towards the goal of really having kinematic structure constants, right, that we could apply at loop level. And then, one thing we did was applying the same sort of functional methods we do to find Jacoby satisfying loop level relations applied at tree level. So using trees as sort of playground to hone our loop techniques. So, okay, now so far I've talked about like rearranging things and yes, getting amplitudes. This actually has consequences. So the original way we were writing numerators where they manifested antisymmetry, when they were antisymmetric, made manifest a certain set of basis relations, known basis relations, in gauge theories at tree level, the Kleist-Coif relations, where there's an n-2 factorial basis, n-2 factorial independent color-ordered amplitudes. It turns out after you impose color kinematic dualities, it makes manifest the fact that these guys aren't actually quite independent. They're related. In fact, it's n-3 factorial independent. These are, so just to be very specific, 5-point has 2 independent color order amplitudes where you fix these 3 legs and you let these 2 vary and you can express any color order in terms of these. 6-point, fix these 3 legs and you let these guys vary. You can express any 6-point color order in terms of these. We conjectured a general formula expressing any n-point color order amplitude in terms of a chosen n-3 factorial basis from super Yang-Mills. This is 2008. This was just conjectured. A year later, and there was a proof from string theory. So these guys found monogamy relations in open string that led to string generalization of these relations, of these Kleist-Coif and n-3 factorial relations, such that when you take alpha prime to 0, you get exactly back these field theory relations. A year after that, we started seeing pure field theory proofs of these relations, bringing the power of BCFW to bear. And just even a few weeks ago, there's a really nice paper by Freddie that proves these n-3 factorial relations in a very slick way. Okay, so another cool thing was understanding the string roots of n-2 factorial, n-3 factorial relations led to a complete pure spinner n-point open string amplitude in terms of color ordered gauge theory amplitude. So this is sort of just a preview for stuff that Oliver is going to be telling you about. But so you see here's a full tree level amplitude of all orders in alpha prime. This is just a pure Yang-Mills scattering amplitude, field theory scattering amplitude. And here are the string effects all encoded in these Euler integrals. And a very recent paper by Ollie and Stefan shows some incredibly deep structure going on here. So there's actually a lot of really exciting stuff. Okay, but back to KLT. I promised a little disentangling of KLT. Okay, so one thing to first note is that what we have here, what was explicitly here, was this n-3 factorial basis. And as complicated as this is, it turns out that now it's proven this is the most sort of compact representation of this type of relations with open strings going to the closed string. Using that, so these n-3 factorial amplitudes allowed the re-expression of field theory KLT in terms of different basis amplitudes, you could choose to make it left and right symmetric if you wanted. These relations allowed proofs of KLT for gravity and gauge amplitudes in field theory by these guys, and generalized monogamy relations, so sort of string theory generalization of these guys, allowed a rewriting of string theory KLT into closed form, their momentum kernel. And so if you take all of these different representations, of course, and you write the color-ordered trees and graph expressions with color kinematic satisfying numerators, you do recover this double copy. And it turns out this double copy is exactly what generalizes to loops. But before I get to loops, this is just really cool. Okay, so just a few months ago, these guys proposed a generalization of the color kinematic duality for BLG theory. And so you've got this three relation here. So instead of a Jacoby with 4, you have a Jacoby with 3 guys. You've got a generalized Jacoby with 4. And what they hypothesized was that as the color obeys this, you can find a representation where the kinematics obey this. This was verified at 4 points, which isn't as significant as the fact that it was verified at 6 points, and the double copy of this guy gives the correct n equals 16 supergravity amplitude in the 3D of Marcus and Schwartz. This is I think a very cool result. I look forward to seeing what comes out of this. Okay, but this is all semi-classical. The world is quantum. Wouldn't it be great to generalize to loop order corrections? And so we ask Jacoby, and he tells us we should always generalize. And so what's the right generalization? It's to do exactly the same thing, right? You write your integrand in terms of cubic graphs, and you conjecture that for every amplitude you can find a representation, a set of numerators, a representation of the numerators, such that every edge obeys Jacoby. So edges map between graphs such that Jacoby is satisfied on all edges among the representation. If the conjectured duality can be imposed for the gauge theory, then through unitarity and tree level expressions, you automatically get the loop level gravity theory. And this is what we always wanted out of loop level relations. So previously the way we'd calculate is we'd take gauge theory trees, use unitarity to get loops, and then you'd have to go all the way through unitarity, back to tree level, through KLT to gravity, and build up gravity loops, right? This double copy lets us go directly from gauge theory loops when we can write it in this color kinematic manifest way, and just by taking a double copy of the kinematics, we get the gravity. And so we know this works beautifully at 1 and 2 loops for n equals 4 and n equals 8. So these are the n equals 4 amplitudes with the prefactor here being 1, and n equals 8 supergravity is simply squaring the numerator contributions here. But the first place where it was obvious that we didn't have right away a color kinematic satisfying representation was our 3 loop, right? So you see here, this is the square of this, but these are not the square of this. And when you look at the amplitude here, this almost satisfies the Jacoby. So if you Jacoby around here, you almost get this plus this, right? But there's extra terms there, right? So this guy spoils the Jacoby. So what you need to find is a way of spreading out this contact guy among graph contributions such that all the Jacoby relations are satisfied edge by edge. And the way to do that is actually really nice. And so every edge represents a set of constraints on the functional form of the numerators. You don't need to take into account all the edges. You only need a small fraction, enough so everybody can speak through each other to everyone else. You find the independent numerators by satisfying those sets of Jacoby relations. You solve those linear equations. Those will be your masters. Those will be the guys who encode everybody else. Everybody else is expressed through Jacoby in terms of them. You build ansatz for what those numerators should be using functions seen on exploratory cuts. You impose the relevant symmetries to the graphs, and then you fit whatever remaining freedom to the theory, right? To whatever information from the theory you need. Okay, and so here I said you didn't need all the edges. These are all the edges you need at 3 loops. So as one thing that was interesting is with just these graphs, you could find Jacoby satisfying numerators, but they didn't fit the theory. They didn't allow for n equals 4. When you expand to all the guys who are related by Jacoby to this, that don't have triangles or bubbles, manifest triangles or bubbles, you include these guys. And each highlighted edge, so this highlighted edge maps between this guy, a guy with a triangle, and then to this guy. So this relates to this guy relates to here, this guy relates to here, and so on and so forth. It turns out through all of it, they ultimately relate to this guy, to E graph. And so if you want to see, these are just the numerator relations, right? So everybody relates to the E graph eventually. It turns out, once you express in terms of those guys, only the maximal cut information, so cutting all the propagators, so just targeting the information for this graph was sufficient to build a full amplitude. And so this is the result. This is the Jacoby satisfying n equals 4 super-Yang-Mills numerators. It's the square root of n equals 8 supergravity. It does satisfy all the cuts. And really interesting, it makes manifest the fact that n equals 8 supergravity has the same overall power counting as n equals 4 super-Yang-Mills. And you can say, how can it do that given that it's a square of things that involve loop momenta? It turns out that the Jacoby representation pushed the worst behavior of Yang-Mills into these guys with external propagators. Now, they're not really external propagators. You see, there's this S sitting here that closes it. This is a way of encoding a 4-point, right? But when you square these guys, their UV behavior doesn't get any worse. And these guys who you push some of their bad behavior here comes up to match what they were originally. So this is how n equals 8 overall UV behavior is the same as n equals 4, even though there's this squaring relation graph by graph. Okay. So other loop level examples. So 5.1 loop n equals 4. It turns out the venerable form, the canonical form that's been sitting in the literature does satisfy the duality. There's no freedom. And so this is the master, and this guy is expressed in terms of him. 5.2 loop n equals 4, n equals 8 supergravity. You can use this guy as a master, and everybody else gets expressed in terms of him. 5.3 loop. Turns out you can use these two planar guys as masters and get everyone, or you can use this one non-planar guy as a master and get everyone. And I'm just showing you who the master is, but we actually found the Jacoby satisfying representation for all of these amplitudes and the associated n equals 8 supergravity representation, and integrated to find the ultraviolet behavior. Okay, so here's the planar n equals 4, and this was written down in 2006. And you notice my earlier slide, I said we didn't actually get non-planar, the full n equals 4 until 3 years later, and it's because there are all these contributions, right? But it turns out that you can use two planar guys to encode the information for all of them, or one non-planar guy to include the information for all of them. Okay, so I'm going to spend a few minutes talking about some cool results with integrated amplitudes. Okay, so I mentioned that, that the two different copies didn't have to come from the same theory, that if you take a theory with less supersymmetry, then you build a supergravity theory with less supersymmetry. Something I didn't stress is that only one gauge representation need to have the duality imposed. This is a consequence of general gauge freedom, the fact that I can change my gauge theory amplitude by any shift as long as it doesn't affect the amplitude. And the way it's not going to affect the amplitude is because it's friendly with Jacoby such that it goes to 0. Well, if it's friendly with Jacoby such that it goes to 0, so I can shift away from a color kinematic representation to a non-Jacoby satisfying representation, right, and still have a valid amplitude. Similarly, since this can only depend on the algebraic properties of this, the fact that this obeys Jacoby, if I replace this with a numerator factor in a gravity theory, then this would also be 0. So I can use a non-Jacoby satisfying numerator as long as the other copy is Jacoby satisfying, the other representation is. this ends up being very, very powerful. Recall 1 and 2 loop at 4 point, there was no loop momentum dependence in the color kinematic satisfying representations for 1 and 2 loop n equals 4 super Yang-Mills. Okay, since the numerators are independent of loop momenta, and so the same is true for 5.1 loops, these numerators can come out of the integrals for the double copy, meaning what's left is the integral of the other copy. And so it turns out there are integrated 1 loop 4 point and 1 loop 5 point n less than 4 super Yang-Mills, n less than 4 Yang-Mills and down to n equals 0 in the literature. These are integrated expressions, double copying with this color kinematic satisfying numerator factor gives you integrated n greater than equal 4 supergravity. And so Zvi and Camille and Henrik did the 1 loop double copy, reproducing the calculations of Dunbar and collaborators in a very, very, very slick calculation. Also, this is kind of off the track, but recently these guys, Dunbar, Edel, and Perkins, have been doing some fantastic work at 1 loop where they have all 1 loop MHV supergravity amplitudes for n equals 4 supergravity. And they went after using soft and collinear factorizations. This is a huge amount of data to try to understand and try to match to. Okay. Now, this actually goes to 2 loops. I said the 2 loop 4 point was also independent of loop momenta. And so, Camille and Lance took the integrated n less than 4 2 loop and went and did the first 2 loop n equals 4 supergravity calculation. I'll point out that the way one of the ways they know they actually got the right answer, there are very strong checks from IR knowledge that soft divergences exponentiate. Okay. So I'm going to close with some remarks on surprises in the UV. So these are predictions and thoughts on divergences for n equals 8 supergravity and d equals 4, sort of through the ages. But you'll see there's one loop order that everybody's converged on, or maybe not everybody, but there's definitely a sort of a consensus in the community that, that there exists a valid 7-loop counterterm, and what that's going to mean is trouble starting at 5 loops. And so this is where the excitement is. Now you can ask, do we have an example of a valid counterterm that doesn't vanish for any accepted symmetry reason? And yeah, there's n equals 4 supergravity at 3 loops in 4 dimensions, and the consensus was that a valid r to the 4th divergence exists for n equals 4 supergravity and d equals 4, analogous to the 7-loop divergence of n equals 8 supergravity. And this is a calculation that was absolutely technically impossible 2 years ago, because the lack of supersymmetry, so n equals 4, half the supersymmetry, doing the gauge theory calculations to try to build through KLT would just be a mess. But due to the fact that that we have n equals 4 super Yang-Mills in a color kinematic manifest representation at 3 loops, let these guys do something really slick. So this is V and two of his students, Tristan and Scott Davies and Yutun Huang. This is an amazing calculation. What they did is they took the n equals 4 amplitude, right, representations, satisfied color kinematic representations, which only involved these graphs, right? All the other graphs in n equals 4 are set to 0, even though for n equals 0, there's a ton more graphs with triangles and bubbles and all sorts of nasty stuff, right? But due to the double copy, they'd get multiplied by 0. So you only have to worry about contributions to these topologies. And since you're interested in going after the worst, the UV divergence, right, you only need to keep track of the really bad behaved Feynman contributions. And so that's what they did. So they didn't build the full 3-loop amplitude. They didn't need to. And they did find graph by graph divergences. Not in these guys. These guys are very well behaved, but these guys all have divergences. And you know, sum over the diagrams is gauge invariant. And when you add all these divergences up, it cancels completely. And this was a surprise for everybody. It was definitely a surprise for me. Maybe, okay, so let me show you two people who may not have been surprised. So Renata wasn't surprised. She's got her thoughts, and it's basically the same sort of argument for why she thinks that there may not be divergent at 7 loops. She thinks applies to n equals 4, and Turkin and Van Hove had an argument as well, and Turkin's here, and so we can ask him more about it. I think it's fair to say that there's not a consensus as to what was responsible for this amplitude being well behaved in the ultraviolet in 4 dimensions. Okay, so there's been sort of interesting recent development of 4 loops. So this was a calculation. The color kinematic satisfying gauge theory giving the double copy gravity theory gave us a gravity theory in a form where the ultraviolet behavior was manifest, and this allowed us to integrate in the critical dimension 11/2. It's the same critical dimension where Yang-Mills diverges, so 11.5 dimensions. And this is what the Yang-Mills pole looks like. And so what is this? This is an integral. This is a vacuum integral. So this is the leading UV behavior. So as external momentum goes to 0, the dots just mean double propagators. This is the leading color contribution, right? This is sub-leading color contribution. You'll notice there are only single trace contributing. And this is a supergravity divergence. This right here, it's the same divergence. So the gravity UV divergence is directly proportional to the subleading color single trace divergence of n equals 4 super Yang-Mills. And this is something that we saw 1 through 3 loops, but here it's particularly surprising because you see how the overall UV behavior, the double copy, it shuffles momentum around, and sure, it's the same manifest UV behavior, but here you actually see it's the same integrals contributing in exactly the same way, and it's tying it to the sub-leading single trace. We don't have an explanation for that. We don't have an explanation for why there's not double trace terms. It's tempting to think it may have something to do with the fact that a color kinematic representation exists, and so somehow sliding through Jacoby's, the double traces cancel. And it's tempting to think that this gets pegged to this contribution because of double copy, but we really don't know. Okay, so status of 5 loops. So we have now finished our n equals 4 super Yang-Mills 5-loop calculation. It's a long time in coming, and we're going to be putting it out on the archive within the next few days. It is not in a color kinematic satisfying form. If it was, we'd already have gravity, and I'd be giving a very different sort of talk right now. But it does have all the information, and we're working towards putting it in a color kinematic satisfying form. In this representation, we have 416 cubic graphs, and we're able to find the ultraviolet pole in the predicted critical dimension of 25/6. And again, no double trace terms, and no single color trace terms beyond the 1/NC² suppression, just like L less than or equal to 4. And so this is it. So, I mean, obviously, if this pattern persisted with gravity having the same UV behavior as the subleading single color trace terms, then it would be finite, but we have no idea, and that's what we're going to go do. That's what we're calculating right now, is going after n equals 8 supergravity. Okay. All right. So let me close down by talking about where we want to end up with these methods. So what we'd love to do, so we see all this redundancy, right? That we were able to express all these graphs in terms of a very, very small number of graphs, contributions of a very small number of graphs. It'd be wonderful to be able to rewrite the S matrix so that these relationships are just completely obvious and you don't have to go through all this rigmarole of tossing things around. And so I think we can listen to Nima's talks about interesting ways about rewriting S matrices with graphy thinking and thinking about geometry. Okay, so this may not happen immediately, right? So what we'd like is a direct way to write down masters, to write down the independent bits of information, write down things such that they automatically satisfy Jacobys. So the kinematic structure constants that extend to loop level. And so there's ongoing work by these guys on exploring this, and I think they have all plus helicity at one loop in color kinematic satisfying way. As an intermediate step to this, we'd be happy with just greater control over moving more fluidly between representations. For example, n equals 4 super Yang-Mills planar is pretty much solved. I mean, getting the planar integrands is pretty much solved, and these relations move information between planar and non-planar, but you have to get the representations in the right form. All right, so being able to move more fluidly between representations is definitely desirable. Generalizations to other theories, like this is fantastically cool thing going on with BLG. Questions about existence in higher perturbative genus string theory that we can learn from Stieberger and Oliver and Carlos. And I think there's other interesting questions, sort of what's a non-perturbative implication or barrier to understanding gravity as a double copy. So there's lots to do, and I'm going to close with just this suggestive slide in the background.
Thank you very much. That was actually very fast. Saved some minutes. Is there any questions?
Okay, I've got a few more slides.
Actually, I have can you extract a 5-loop cusp from what you just?
What was it? Say that again?
5-loop cusp. Can you get it from your calculation?
Do we have 5-loop n equals 8?
No, for n equals 4, can you get the cusp dimension?
Oh, the cusp. No. Well, so that would require integrating in 4 dimensions, right? And no, we can't even do the full 3-loop integral for the non-planars at 3-loop in 4 dimensions. But I mean, those that do integrate and do serious integration are progressing faster and faster. But we're not at 5-loop. We've had 5-loop planar for a long time, right? And haven't done integrals.
So you need more time for it?
I'll take it. Yeah, let me just. Okay, so. Okay, this is kind of cool. So there's something to think about in terms of how efficient these sort of encodings are, right? So, as I said, it's kind of weird and a little backwards to start going to graphs after all these incredibly compact, spectacular representations of color-ordered tree amplitudes. But it turns out that the efficiency isn't that crazy. So so you start with these graphs, but only n-2 factorial numerators are unconstrained by color kinematics. So these are the guys that could be your masters, right? You have n-3 factorial distinct color ordered amplitudes. These are the number of unique topologies that exist as multiplicity increases. But the line I want to draw your attention to is this guy, right? And this is 1, and it's a fact that there's one ladder topology at every multiplicity. And all cubic trees can be expressed in terms of ladders. So if you have one numerator function, so like so our loop level amplitudes are symmetric in the sense that it's one function for a graph, taking whatever the external labels are. It's one function taking it to the kinematics. If you have that same type of thing at one loop, then you really only have one numerator mapping for every multiplicity. And that's an incredible compression of the sort of information you need to be carrying around. So I think that's kind of interesting. And so that's something that we've been poking around with a little bit, is exploring these symmetric numerators at tree level. And it turns out in going after these symmetric numerators at tree level, you expose yourself to a lot of the complexities that you get with solving these functional relations at loop level. So so this symmetric tree level is a kind of playground for looking at higher loop stuff. But I won't take up too much more time. Yeah, no, I can close here.
What was the dimension you found for the divergence of the 5-loop problem you described?
The 5-loop Yang-Mills?
Yes.
Yeah, it was 26 over 5.
Because it looked different.
25 over 6.
26 over 5 sounds better.
26 over 5. I'm sure I made a typo, yeah.
Thank you.
Further questions? Hermann?
I have one more clarification. It's 25 over 6. That comes from the d equals 4 plus 6 over L.
Okay.
And that's supposed to be
yes.
where the onset of divergence is, but now you write it's even finite for that. Or wouldn't you expect it to start diverging at 25 over 6?
Right, sorry. It is the critical dimension of Yang-Mills, right? And that's, right, so 4 plus L over 6. Yes, it is 25 over 6. Sorry, 4 times, yeah.